Hello, I'm Erik Altman, Editor-in-Chief of IEEE Micro magazine. Processor reliability has long been an important design consideration. However, as device sizes shrink and other factors such as power grow in importance, the challenge of designing error-tolerant chips increases. However, the set of techniques by which reliability can be addressed has also increased, including techniques at the device level, circuits, microarchitecture, system architecture, and software. In July-August 2013, IEEE Micro devoted a special issue to reliability-aware microarchitecture. The guest editor for that issue was Professor V.J. Reddy of the University of Texas at Austin. As testament both to Professor Reddy's efforts and the importance of the field, we received almost 30 submissions, of which we could accept only 7. Those 7 submissions illustrate the wide range of techniques now being brought to bear in reliability problems, and I will briefly describe each of them. In the first paper, Capuzzo et al. Addressed reliability challenges when operating at near-threshold voltages, i.e. when the supply voltage of the circuit is only slightly higher than the voltage at which the circuit switches from 0 to 1. There is great allure in going to such near-threshold designs because they have the potential to vastly reduce power. Alas, the proximity of the supply voltage and the switching voltage greatly increases the challenge of robust operation. In particular, individual transistors tend to have a much wider range of operating characteristics such as maximum frequency than do traditional non-threshold designs. To tackle these issues, Capuzzo et al. Propose Energy Smart. Energy Smart employs multiple frequency domains on the chip, each of which can be individually controlled to handle transistor variation. Capuzzo et al. Find that Energy Smart generally performs as well as or better than traditional, more costly approaches. In the second paper, Wang and Kim take a very different approach. They target carbon nanotube devices and actually decrease redundancy at the transistor device level compared to traditional designs. However, this reduction is in service of allowing smaller, faster processor cores. The smaller cores, in turn, allow more cores, which can be used to provide redundancy at a coarse grain level. Various configurations are tested across a variety of parallel benchmarks, and in most cases, the coarse grain approach is very effective. In the third paper, Palfreman et al. Also use a relatively coarse-grained spare ribs approach, which provides a relatively small number of redundant intermediate bit slices or ribs in the logic data paths. For example, an 8-bit adder might have 10 slices, 2 more than the necessary 8, with the ability to switch the extra 2 slices in place of any of the other 8 slices that have a defect. Palfreman et al. Show that this approach can be employed without a reduction in frequency compared to a traditional design, and that depending on the number of spare ribs, fault coverage can be made nearly equal to more traditional approaches, but with considerably better power performance. In the fourth paper, Leffergy et al. Observed that most processor designs have a large guard band, i.e. they operate at a higher, more power-hungry voltage than necessary to ensure operation remains correct in all but the most stressful operations when voltage may drop below its normal intended value. Instead of always having this high guard band, Leffergy et al. Proposed constant measurement of how close the chip is to violating timing constraints, for example, when a signal arrives too late to be used. Operating voltage can be dropped when timing constraints are comfortably met and increased otherwise. Leffergy et al. Performed experiments on IBM's Power 7 and Power 7 Plus chips. The proposed approach was found to reduce power by 11% while actually increasing reliability over the baseline. In the fifth paper, Kleiberger et al. Focus on the reliability of memory and wireless systems in a 2-wheeled robot. For memory, Kleiberger et al. Examines single-event upsets in which an atomic particle hit, gamma ray, or other factor causes the value of a bit to flip from 1 to 0, or vice versa. Such bit flips could be addressed with extra bits in the memory, for example, with error-correcting codes. Such bit flips could also be addressed at the software and algorithm level. The essential requirement is that the robot never deviates significantly from its intended task, a result that does not always require full fidelity of all memory bits all the time. In the end, Kleiberger et al. Find that higher-level, less power-intensive techniques provide almost as much protection as low-level mechanisms that provide 100% memory fidelity. In the sixth paper, Zafarin et al. Also addressed single-event upsets, flipping the value of a bit. They observed that with shrinking device sizes, a single particle hit is likely to impact more than one transistor on a chip. To deal with this problem, Zafarin et al. Developed the Svalin network so that chip designers can examine likely problems and cost of different techniques for mitigating those problems. Here, cost is measured by some combination of chip area, frequency, power, and energy. In applying Svalin to the open RISC processor core, Svarin et al. Find a wide range of costs among different mechanisms, underscoring Svalin's utility. In the seventh and final paper, Kim et al. Focus on tooling to help designers. In particular, Kim et al. Note that electrical current varies over time, something that can create timing errors due to voltage drops. Such timing errors are one of the same problems targeted by the guardband network of Leffergy et al. That I described a little bit ago. However, instead of having a variable guardband, Kim et al. Develop a stress mark benchmark designed to show ship designers the worst-case variations and let designers adapt designs to those variations. Such adaptation is illustrated with the floating point unit of a processor, since floating point is normally one of the most sensitive parts of a design for voltage and timing issues. I hope that this outline has given a flavor of the class of reliability problems facing chip designers and some of the potential solutions to those problems. Of course, these brief descriptions cannot do justice to the full field and set of papers. If you have further interest in this exciting area, I hope that you will read the papers from the July-August 2013 issue of IEEE Micro and additional work beyond. Thank you for listening.